Good afternoon, everyone. My name is Sim with the ABC Commissioning Group, and I'm here to welcome you to another ACG Essential Commissioning webinar series. This is our fourth year hosting a webinar every month from July to December, and we are excited to provide a fresh new lineup on topics related to the commissioning process. We'd like to do a special thank you to CX Planner for sponsoring this particular session. I'd like to go over a few housekeeping notes before we get started. The presenter will be holding the questions until the end of the presentation, but we encourage you to submit them at any time using the happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists, and our technical experts will assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of the CEUs, that is the continuing education credits, everyone in attendance for the full webinar will receive a certificate of attendance sent to their emails within 24 hours. And finally, if you are a certified CXA or EMP, your CEUs for attending any webinar in the series will be automatically uploaded to your respective portals after the final webinar concludes in early December. Today's webinar is Building Electrification Commissioning with Brendon Mattis. Brendon Mattis started his career working in the design and construction group at the University of Missouri in the early 1990s, with an interest in energy conservation and how buildings really work. This interest led him to Seattle, Washington, to begin his career in building commissioning with EEI. With 30 years of experience delving deeply into how buildings work, he has learned many lessons the hard way. Hopefully, today, we can share some stories, concepts, and ideas to move the building performance forward. Thank you, everyone, for joining us. And with that, I'll hand it off to Brandon to kick us off. Take it away, Brandon.
All right. Thank you. Welcome, everyone. Glad to be here today. We're going to talk a little bit about building electrification and kind of the why and the how. What are we doing here? What can we do? And there's certainly a bright future ahead of us. Learning objectives. So we want to describe the goals of building electrification, recognize the near-term emission impacts of building electrification, and discuss the challenges of building electrification design and operations, kind of on the real world side, what's happening. And through this, we'll identify some strategies for building electrification projects and what the role of us as commissioning providers, how we can help get there, help achieve decarbonization. Small shifts make a big difference. What we're seeing now is the global average temperature is slowly increasing, and it's creating a lot of strange events across the boards. We're seeing more extreme hot weather. We're also seeing less cold weather. Ski seasons are getting shorter. Snowpack is decreasing, lower water levels in a lot of dams, that sort of thing. So these relatively small impacts can really throw the planet off. We see it every day. New high temperatures broken. I think 2023 was one of the highest average temperatures that we've ever seen. So it's going up and up and up. And I think we're about little under 1.5 degrees C right now, but I think there is hope that we can maintain that. What's happened, this month we're seeing, record low levels in Lake Mead, regular fire seasons in the West, doomsday glaciers, the list goes on. I think this year we've actually had a pretty quiet hurricane season so far. What can we do as commissioning providers to help the climate? We'd like to explore that today. What's happening and what are the efforts that we can do to, what are the efforts we as an organization can do and what we can do individually. Why the climate change is becoming a big deal. NOAA's created a graph of the cost of these billion-dollar disasters. So, year over year, we're seeing, natural disasters happening, and they're very costly. So that's causing the banking and the insurance sectors to get very worried. The cost of these natural disasters are going through the roof. It's becoming an existential threat to our economy. We're seeing insurers not wanting to insure homes in California or homes in Florida. They're just, it's becoming too costly for insurance companies. over, since 1980 to 2000, the average annual cost of a disaster was around $54 billion. In the last 5 years, that skyrocketed to over $155 billion annually. So the cost of these things are really going up, and we've had some really extreme years within that as well. So yeah, the financial, the banking, the investment sectors are getting worried, and they're starting to put money back into buildings and really earmarking that. They're no longer climate deniers. They're all in for doing this. They know they need to decarbonize. They know they need to invest in these things. Now we need to marry up the dollar folks and the big money folks with what's happening on the ground. This is a graph that's been provided by Architecture 2030. They have some really interesting research and kind of where we're at from a building sector emissions standpoint. What are the goals that we have ahead of us? Ed Mazaria, the founder of Architecture 2030, has some good content around that. Some really interesting things that we can do in the building sector. Right now, the U.S. emits about 1,500. The U.S. building sector emits about 1,500 gigatons of carbon annually. To do our part, we need to reduce that by about 1,000 gigatons, and we'd like to get to around 500 gigatons by 2030. We see, so it's starting to go down. We're seeing it happen currently. The building sectors are reducing energy. I worked at the University of Missouri, and they, kind of had an energy program from the early 90s where they began to build more, but they really invested a lot of dollars back in their facilities to tune them up, to do building tune-ups, to clean them up, to meter, and then get some new concepts on how they could reduce energy. And, that campus added millions of square feet and actually reduced overall energy consumption. I think we're seeing a similar thing across the U.S. We're adding millions of square feet, and we're seeing a reduction in CO2 emissions. So our efforts are making an impact. We just have a little bit farther to go. What's the probability of getting there? What are we doing right? This is the global carbon budget. So, global CO2 emissions. This is in gigatons again. So the peak was about 40 gigatons, and we reduced significantly to date, but we still have a long way to go. So the projections that Architecture 2030 is making is that we need to reduce our CO2 outputs by 65% by 2030. And there's a 67% probability that we get there. So we're starting to see an impact, and it's starting to make a difference. So what are we doing to get there? We're seeing all electric new designs. So a lot of our new buildings are all electric. We're seeing a lot of increased efficiencies. There's, I think 10 years ago, we really weren't even talking about the EUI of buildings. Now we are. I think now all of us know what kind of the different sectors and what the EUIs of these buildings are. What's the target? Where should we be at? So just that thinking has come a long way. The Inflation Reduction Act is certainly helping. We're incentivizing carbon-free electricity by providing some taxes to large corporations, kind of a carrot or a stick. Right now, we're using carrots. We have incentives versus carbon taxes and that sort of thing. So trying to invest in clean energy and clean energy infrastructures. The United States is providing about $400 billion in this over the next few years, trying to get by 2030 to really make that impact on reducing the CO2 output of our industries and our buildings. And that's, they're investing in the production side and also the development side in industry as well, battery plants, electric cars, heat pumps in your houses, that sort of thing. We're seeing a large increase in the generation side from geothermal, wind, electricity. There's even discussions now about smaller, more scalable nuclear as well. So I think that all options are on the table, and we'll talk a little bit about what the differences are between each of those. So where are we at today from a global average surface temperature? We've gone up significantly. I think this year was the hottest year on record, but we're a little bit over 1 degree. I think this last input of this is in 2020. So 3 years on, we continue to increase. What's the sources of the greenhouse gas emissions? So the transportation sector is about 29%. The world we live in, the commercial and residential buildings, we're about 13% of those carbon emissions in the world. Industry and electricity making up about the other half of that. We really need to work on, the electricity, the generation side of it, and we'll talk a bit about what's happening there. U.S. wind generation. So the U.S. Energy Information Association, the AIA, in 2010 predicted that we would have, a much lower amount of wind production than we really have now. We've probably doubled or more wind production than we thought we would have even 10 years ago or 15 years ago. The wind generation has picked up significantly, providing that sustainable electricity to our grid. Similarly, on the solar side, so solar electricity, the EAI, just 10 years ago wasn't super, optimistic about how much energy we could produce with solar, but we've seen that again take off exponentially. So we're producing, we've gone from a prediction of, not a whole lot to over, 180 billion kilowatt hours of solar electricity. And I think if you drive around the country, you drive around different places, you see more and more of the wind generations, the wind turbines. You see a lot more solar installations. So it's happening. Why is it happening? What's driving this, increased production? It's really the cost. The cost of solar has gone down by about 90% in the last 10 years. The cost of batteries has significantly reduced by the cost of 90% as well. Wind has taken a significant reduction. We're about 3 times less cost on the wind side. So that, this cost structure really changes the whole game. What we didn't think was achievable is now within our grasp. And we'll talk a little bit about how much energy we need to produce. But, given, I heard a comment the other day, someone said that money talks, but politics shouts. And I think what they mean by that is, there is really the political energy is into doing this now. I think people believe that, hey, it's affordable. It's less costly than, installing new, coal plants or gas turbines, that sort of thing. So as we can deploy this, it's more deployable. It's starting to happen. It's within our grasp. And we're seeing real investments in this, creating new clean jobs, clean energy production, infrastructure projects. So there is a lot of that going on right now. I think there's maybe the holdup on some of these things is just getting the permits to do what they want to do to get these installations connected to that grid. In the last year or so, nearly 28 gigawatts of new U.S. generating capacity is added in 2021. A couple of years old on this slide, and it's been led by wind and solar. So that's what's really leading the market right now. Is from a new capacity standpoint, is wind and solar. We added, 30 megawatts of new generating capacity. That's 12% than the year before. So we're really seeing large investments around the country, and you can see by some of these kind of dots where that production is happening. So real money being spent doing real things on that sustainable infrastructure standpoint. This chart kind of shows where we're at, U.S. electricity generation from 2010 to 2034, again from architecture 2030. But the line on top is kind of the total generation. So we're about 4,000 billion kilowatt hours consumed annually, and there's some projections as well that we'll need to double the size of the overall grid to accommodate all the electrification that we're doing. So as we add new buildings, as we move from gas heating, a condensing boiler, something like that, to heat pumps, now we're going to have more demand on the grid. That grid needs to grow. We need to provide clean energy on the backside of that as well. So we'll need to rebuild the power grid. So it has taken us 90 years to build the power grid that we have today. We're going to need at least 1x or 2x that in the next, by 2050 for sure. So there's going to be real investment needed for, expanding the power grid to support our buildings, to support our industry. So what does this mean for commissioning? Electrifying these buildings, over 40% of building CO2 emissions are from buildings that are over 50,000 gross square feet. And that's less than 2% of the entire building stock. Those are the buildings that, you've got large hospitals, data centers, laboratories, that sort of thing, our university buildings, a lot of those are over 50,000 square feet. And most of the building CO2 emissions come from those buildings. So there's some real incentives now to zero in on the larger buildings to start to decarbonize those or electrify those as well. And we're seeing more and more programs there's kind of goals from a corporate level. There's goals from a state level to really, push into these buildings and identify, which ones are the big users and which ones do we need to use. So, yeah. All right. Some technical difficulties. All right. Can you guys still see me? Apologize for the interruption. Sure. All right. Yes, see that screen. Move on to the next slide. So yeah, decarbonization goals. So on the, all right, we're good. From the state, from a global level, the Paris Accord, they have a decarbonization goal by, getting to carbon zero by 2050. And, Amazon has a similar one to get there by 2040, the 2030 challenge, getting to carbon zero by 2040. Google, again, carbon free by 2030. That's just a few years away. That's a large goal. And I think they're making big inroads by buying RECs and that sort of thing. So it's starting, we're starting to see more and more happen on the development side. Big dollars, big industry is really investing in decarbonization. We're seeing, some of these companies develop their own wind turbines, develop their own solar to really help, reduce the grid decarbonization. State and local carbon reduction goals. What we're seeing on a state level in Washington State for sure, I'm very familiar with that program. But the Clean Buildings Act there has, required that all buildings report their energy use. And there's kind of an energy target developed by building sector, whichever one your building lives in. There's an EUI target that you have to get below by 2025, 2026 or beyond, depending on the size of your building. So there's real goals, there's real impacts to that. We're seeing it's $1 a square foot is the penalty if you don't get below that goal. And then those targets will be reduced, every 5-year cycle. So it'll require buildings to get more and more efficient to get there. We see similar things in Colorado, Virginia, Washington, D.C. as well, and New York City. I think it's the local law 97 might be pushing some of those similar things there as well. So lots of investment from the Fortune 500 companies and also from the state and local carbon reduction goals are, becoming into play. Commissioning is a big part of that. So we are the first round of what can we do in these buildings to get where they need to go. So what's the focus on building electrification? So that was kind of the previous stuff was kind of why we got to the point we're at now, and how does this affect us as commissioning agents? What's the opportunity going forward? How do we kind of help owners achieve their goals and get to where they want to go? They have a good idea of where they want to go. Maybe the building details and the minutia is where we step in to figure out, okay, what's your building doing? How can we get there? Where do we start? From a new building standpoint, do it right from the beginning, do it right with the design. And we're seeing that over and over. Most of the buildings we're seeing now are largely electrical, maybe some backup, some emergency, and some either diesel generators or natural gas, water heating, that sort of thing. Existing buildings is probably the biggest opportunity that we have as commissioning agents. So 1% of the building stock is renewed any given year. 99% of that that remains is existing buildings. So there's a lot of buildings that are getting older, and we'll talk about kind of some of the work that we've done with Seattle schools and what how are they going to address that? How do they roll in new building construction, and then the decarbonization, electrification on some of their more recent projects that they've installed in the last 10 years. Transitioning current fossil fuel spaces and their process heating to electric power, that's kind of job one, is starting to install those heat pumps. Looking at some, there's a lot of different things, a lot of different heat pumps, a lot of different solutions you can look at from a design perspective. But really, how do we optimize what we have as a good start? The trickier parts, humidification, sterilization, cooking, those all get a little bit more difficult. And generators, do you get rid of those generators? Do you keep them? How do you deal with that? And I don't think we're quite there with batteries yet, but maybe eventually batteries. What are the steps to reduce CO2 through electrification? The first is efficiency. If we can reduce that load, that's where we want to start. So we want to start, with insulation, maybe some window shading, putting new windows in. Envelope improvements are very important for reducing all energy use. And we see, you compare a building built 30 years to a new building today, just how tight the envelope is, and that leakage reductions makes a huge impact on your energy use. So that those drafty buildings, those have an impact from an energy use standpoint. Ventilation, it's another place. Going through COVID, we've seen a lot of things happen, from decreasing ventilation, maybe for demand control ventilation, with COVID going through. Now ASHRAE is looking to push that up from a ventilation standpoint. I think optimizing that, how do we have much better monitoring now. We have PM10, PM5 sensors we can put in buildings. We can not only watch the CO2, we can watch the particulate, what's happening in these spaces. So now we can start to really track our ventilation with what's going on in the building. Heat recovery, we see that a lot of times with, just exhaust air, recovering that heat, like go to heat pumps, efficient distribution, energy management. And you get in, lighting is always a big deal. If we can reduce lighting loads, now we're reducing cooling loads, heat and cold storage. So all of these things from a design perspective have big impacts on how buildings use energy. And we just, from a commissioning standpoint, as we can help optimize those sequences in the design, review those, help the designers write better sequences, is probably the best thing, the best time spent from, an overall building performance standpoint. So what steps should we take? First is improve building efficiency. If we can reduce that EUI by looking at runtime hours, heat recovery, maybe some simple fixes, low cost fixes might include heat recovery, that sort of thing. I got a note up here. Shift in electrical generation. We've also have to work on the production side of it as well. move away from coal and gas and move more towards the low carbon sources, PV, wind, solar, hydro. That's not always the best answer. And we'll talk about, what's going on the grid side. As we electrify buildings, we have to be conscious of what's happening at the grid as well and consider that mix of what we have. The time horizons for electrical generation. What we see now, as we get further out in time, we'll see more and more use of those renewables. The short term, we want to, right now we're using all the low carbon sources that we can. We want to, have more and more penetration of those low carbon sources and continue to peak with the natural gas, the coal, as we increase the sustainable resources and decrease the overall. The middle term, we want to base load with the low CO2 and then peak with those higher, at a less frequently. In the long term, base load all with low CO2 generation and peak with storage. So batteries become a big deal as we move into the future. So what on the generation side, fuel input matters. So it was something that kind of took us by surprise for some of the projects we did with the GSA. But, if you look at it from a source standpoint, gas or coal, you have 3 units of input to make 1, kilowatt output. And that's where you get a lot of the CO2 emissions. Gas turbines, similar, you've got 4 units of gas input and 1 unit of output. CO2. The good part of gas turbines, and you see a lot of that with peaking plants, is they have a quick response and their emissions are relatively low compared to coal or gas. Nuclear, that's something that we're looking at going into the future as a country. But I think that the question there is you still have the production of the fuel, and then what do you do with that waste at the end of it? That's probably the biggest question on the nuclear side. Whereas wind, solar, PV, low fuel inputs, it's all sustainable, natural, environmental, and, you get electricity out the other end. From a building heat production standpoint, so now we're using this power we've created on the grid. How do we move that into the building? Heat pumps are a great way to go, or heat recovery chillers, maybe less so, but heat pumps, if we have decent ambient temperatures or a consistent source of heat, then those are great. Some of the limitations of heat pumps are, what do we do at low temperatures? What do we do when it's cold outside? We need to get a little bit creative around that. We'll talk about a bit about that in a second as well. Building heat production and energy input. So, from a, what NZs versus outsies, what's that EUI, not the EUI, but the coefficient of performance. So a gas boiler, you're going to have 1.1 units in of natural gas to get one out. Along with that comes the site CO2 emissions. Electric resistance heat sounds like a great idea, but when you think back to that source energy, where are you getting your power from? It might, just burning straight kilowatts to make heat probably isn't the best use. Now you've got 4x on the other side of what you provided. Heat pumps become, more and more effective. So now, your coefficient of performance is somewhere between 2 and 4 units of output when you have decent ambient temperatures. You get to colder climates, you see more and more ground source heat pumps. If you have a stable ground temperature, looking at your aquifers, what's happening underground, how much energy can you reject to that space. Again, you get high efficiencies on ground source heat pumps. For every unit in, you get 3 to 4 units out. Some issues with the ground source, you could have some limitations. If you're only pulling heat out of that, you're going to cool your your ground off over time, lower that temperature. We see that a lot in Seattle. We don't have a very long cooling season to kind of recharge that that volume of earth. But something to be aware of as you design for the long term, and from a commissioning standpoint, how do we operate this building? Do we have enough heat going back into the space? Heat recovery chillers, again, if you have a stable source, they're great. What we see a lot in buildings with heat recovery chillers is they don't have a stable source of heat. As buildings load up, unload, there's a lot of variability that is there. And heat recovery chillers like to have constant flow, constant temperatures. They just want to chew on a load and spit out heat out the back end. But if that load changes, or maybe that load didn't show up as you occupy the building, we see problems with chillers tripping on a low temperature. So we've got to be aware of that. We've spent a lot of time trying to fix heat recovery chillers just to get them to run continuously. Not all electricity is created equal. Something else that kind of, I became aware of after doing a few projects, kind of looking at, what is the CO2 equivalent of each of the regional emission factors. You look at upstate New York, they have a lot of hydropower up there, so they've got a lower CO2 output per unit of electricity. You get to the Midwest or the Southeast, where there's a lot of coal that provides a lot of their energy. Now you're looking 150 to 200 kilograms of CO2 per MMBTU. The Northwest, which is a large area, there's a mix of hydro and natural gas and coal out there as well. We've got a little bit lower of a number there. You get into Seattle, we've got a very low number, because that's what's hydro is primarily the source of power for us. So it's a very low CO2 impact. And natural gas often is a pretty clean source. If you're using it for heating in a building, now you're using that heat directly. You've got a condensing boiler. You have less impact. If you're using electricity for heating that's produced by a coal generating power plant, that might not be the best thing. As a temporary measure or as a phase or a step in your process, looking at natural gas might be an okay reduction in CO2 emissions for your building. Speaking of the emissions factor, so as we kind of put all of this calculus together between the production side and what's happening on the use side inside of the buildings, natural gas emissions, being at 53 kilograms per unit of heat output. When you kind of look at all the different options, if you're going to go to the average United States, let's use electric resistance heat to heat your building. That could be an electric boiler, that could be strip heaters, that sort of thing. You have a 2 times impact on the emissions side. So not only are you using this electric heat to heat your building, but now you have to think about those emission factors, and it's probably way worse than natural gas. You get into a low emissions, electric resistance heating can be half of what natural gas might be. In a high emissions, you get to Oahu, electric resistance heat has a really big CO2 impact to your environment. So probably not the best use of electrical power. Air source heat pumps. So now we have a COP of somewhere between 2 and 4. And you've got the emissions factors of 118. So it's maybe about half or break even to natural gas emissions. You get to the lower emissions, now it's a quarter to an eighth. You get into high emissions, even the air source heat pump, you might be better off to go with natural gas. Will have a lower CO2 output than an air source heat pump if you have a high emissions area. Heat recovery chillers, now we're getting more efficient equipment. And how does that compare? How do we compare that to natural gas emissions? It might be getting better there as well. So if you have a low emission source, it could be significantly less to use that heat recovery chiller than to use natural gas. So how you mix all of your energy sources and your equipment on site, just think about that, and the CO2 emissions from a broader range. It becomes important. So the electrical grids, so kind of all of the grids are connected to some degree. What we see is, the renewables are used first, and we see that, that's going to be used. We're going to use as much wind, we're going to use as much solar as we can. So it's kind of a zero-sum game. I mean, we're using as much as we can produce. That impacts the peaking plants, those natural gas plants, the coal plants. They have to react to how much renewables are being put on the grid. In short term, there's marginal increases over the overall electrical load are met with those high CO2 sources. So, we might baseline with as many renewables as we can, but we're still going to use, the high or the medium CO2 emitting sources as we go forward. If we can start installing, low on-site, low emissions on-site systems, solar, wind, that sort of thing, that would be ideal. And then, but efficiency becomes kind of the key for what we want to do here. The challenges in some of these, I'm going to have to speed up here a little bit. I only have about 10 minutes left. Cold climates. So what do we do with heat pumps and cold climates? We did hear a story about New York City, where they're starting to dig wells for ground source underneath these buildings. So they have short drill rigs that they're trying to drill holes underneath and really kind of tap into that bedrock to provide a heat sink. So, that's one way to offset the challenges of cold weather. Heat recovery chillers, scabbing off as much of that rejected heat as you possibly can. That'll certainly help. Cold weather becomes a challenge. Heat pumps don't perform particularly well when it's cold outside. Case study in cold climates, the Princeton Central Utility Building. This is a building where they basically built a new central plant to serve a new campus they're building, and a very creative use of ground wells, cooling towers, and thermal storage. They also wanted to centralize it. We're seeing more and more of that now. Centralizing this equipment has a big impact to operations. We see a lot of universities have chillers in every building because they've got some special experiment going on. But if we can centralize that equipment, we're better off from an efficiency standpoint, reduce maintainability, reduce maintenance, maintainability, redundancy, staging gets a lot better, and the reliability of less equipment to deal with. This is a one line of their central plant. So they have a series of wells, geothermal wells that are out in the system. They circulate water through there, and they pick that water up and send it to heat recovery chillers. And that produces both heating and cooling, depending on what the demand is. They also put thermal storage tanks in for low load conditions to kind of, if we can keep that equipment off for as long as possible, rely on those tanks. That will help the redundancy of the equipment. And when you get to peak loads, they also have some condensing boilers to deal with that peak when the ground loop isn't able to provide everything, and cooling towers on the other side as well. They started out with a smaller system, and as they grow that campus, they'll add more and more equipment to that. That job's just getting commissioned right now, actually this week. Commissioning recommendations. So what can we do as a commissioning standpoint? We need to improve our building efficiency so we can have a very direct impact for improving building efficiency. We're seeing a lot of monitoring-based commissioning happening out there. I think from an existing building, a retro commissioning standpoint, I wouldn't commission a building without analytics. It just gives you so much better of a view of what's happening in those spaces. And you can, go back, look at, 2, 3 weeks ago, well, what happened when the outside temperature was this, and you can, see how equipment stages. Did it stage correctly? Did it, there's just, it gives you a much better window into everything that's happening. Commissioning recommendations: don't let perfection be the enemy of progress. I think we see this over and over, kind of an ideal of what we want to do with the building, but that may not align with what the owner wants to do. We've looked at a few buildings where we're looking at, okay, maybe not be able to do the whole thing the way we want to do it today, but if we can address lowering those heating water temperatures, maybe we go from a 180-degree water system to a 120-degree water system. That might mean there's, more pumps, more pipe, changing out some coils. But that's maybe a great first step, and keep the gas boilers there, and deal with the chillers later. But just start somewhere to do every little bit that you can that meets the owner's budgets. And evaluate technologies as they go forward. Right now we're seeing new CO2 technologies in heat pumps that maybe those can create 180-degree water. Kind of new technology, somewhat untested, but I think there's a lot of great development happening there. And at the end of the day, I think if we can utilize resistance heating sparingly, we're going to be kind of CO2 ahead for the long run. Complex building systems, we see now more and more energy efficient buildings are happening. We see complex building systems. We've got to be really careful with those. If we have the operators spending more time trying to keep these buildings running, then all of our energy efficiency is kind of out the window. So we've got to maintain a balance of simplicity. And operators, they might run 20, 30 different buildings, and to come into your building and try to figure out what the heck's going on when something fails, and it can kind of be mind-boggling, and they just don't have the training and the expertise to deal with some of these systems. They're overly complicated. So simplicity has value. Please work with your engineers to let's make it simple so the operators can deal with it 10, 20, 30 years down the road. A couple of examples. We'll hit the highlights, running close on time here. Federal office building. So some lessons learned there. A phased approach. So, do what you can with the budget that you have now. Look at lowering those water temperatures, optimizing sequence of operations, heat recovery, do that first, and then we'll go on to the next part later. By switching from steam to locally sourced boilers, we're reducing the CO2 impact by 25%. As we add heat pumps or a hybrid system on top of that, it lowers that CO2 even more. The cost begins to go up. We looked at an all electric option, scraping off the existing plant, putting a new one in. From an energy saving standpoint, the payback was about 250 years, and a hybrid heat pump system was about a 20-year payback, and had significant CO2 reduction impacts as well. Seattle libraries. So there we had 25 buildings under 40,000 square feet, all sorts of building or system types in these buildings. What we looked at doing there from an electrification standpoint is we created a 10-year plan. Number one thing is, putting in energy recovery on air handling units. So how do we collect that heat? And then, reducing those loads with heat pumps. So heat pumps and energy recovery, those Daikin units do a great job of that. Kind of a premium cost, but have payback over the long run. City of Seattle, again, I think some lessons learned there. Emergency generators, paint booths. There's some weird stuff in there that you've got to deal with. I think what we've learned there is maybe you keep those emergency systems as you electrify the building. Maybe when batteries come into play further down the road, you can start putting battery banks in to accommodate that emergency generator. But right now, they're there, they exist. Probably not a lot of reason to get rid of those due to the small duration that they're utilized. That was a lot to say in a short amount of time. Probably a lot of questions out there as well. I think at the end of the day, we as commissioning providers, it all starts with building optimization. We know how buildings work. We know how to optimize them. It's a matter of, bringing the team together to figure out, what's best for the owner with the owner's dollars that they have today. And I think we as commissioning providers have the skills to make a difference. It's an exciting world we're moving into. It's kind of what I entered this business for, is to make that difference. So yeah, with that, I'll open it up to questions, and yeah, thank you guys for listening.
Thank you so much, Brandon. That was a lot of information, and we can see a lot of people come in with the questions too. Perfect. So let's begin with the first question. That's by Barrett. He says that these charts are great. One thing I've been looking for is something that shows the per kWh cost of grid-connected solar versus solar with battery backup. Are you aware of any resources that show the premium to add battery backup versus net metering only setups?
See if I can read that question. So on the battery backup side, I've not seen a lot of industrial use of battery backup to date. Yeah, so I don't think I have an answer for that question. Where can I read that question at is?
You just have to go ahead and look for the Q&A button. So you
there
should
we
be,
go. There we go.
yes, so all the questions should open up.
Yeah, so the first question, I don't know what that premium is for battery backup. I can't speak to that right now, but I will follow up and get an answer back to you.
Perfect. For the second question, we have a question from Paul. He says, what about development of pink power alternatives and SMRs in this country?
I'm not familiar with the pink power concept. Maybe I could get a little more background on that.
Got it. The next one is by Roger. He says, is it the job of the design engineer or the commissioning professionals, to reduce the CO2 emissions? If it is the job of the design engineers, then what is the job of the commissioning professionals towards this goal, and how can they help to achieve it?
Yeah, I think that's a fair question. I think that's a good question. I think we do see the design engineers focusing on a lot of this. I think with our clients, we're helping them kind of in the initial phases to identify what their reduction in CO2 could be. May not be getting to the final design, but just from a conceptual standpoint of what we can do with the building systems, with our knowledge of these building systems. I think we often work closely with the building owners. They come to us and say, hey, what can we do here? So it's a little bit of design, it's a little bit of commissioning to kind of marry both the operational side. I think where we've entered this is on the retro commissioning. As we retro commissioning a building, we're looking at what's in there, what's working, but the owners also want to know what the next step is for their building. So helping them identify what systems they could put in place or kind of what concepts they could use going forward can be very helpful for them. Yeah.
Perfect. The next question is again from Roger. He says, how can you improve the building energy as a commissioning professional during the construction phase?
I would say before, if we're doing design reviews, that's where I think the awareness of when we put together that owner project requirement, to understand what the CO2 goals are for the building, that's becoming a big part in the LEED or the USGBC green build, that sort of thing. They are, embodied carbon is a big buzzword. What is the carbon use of that building? And as commissioning providers, if we can, we're helping develop that OPR, we can definitely influence that piece of it. And then on the operations side of it, how do we optimize the building for CO2 emissions? I think it's good to understand kind of not only the site use of CO2, but the source as well. What is the source in your building, and where are we getting the power for that? And from an optimization standpoint, what can we do to reduce energy use overall? And, maybe, if we have a choice of a gas hot water heater as a backup to your heat pump, how do we optimize the operation of that heat pump, and think through what that means for your building?
Perfect. And the last question that I see here is, how are we going to achieve the zero CO2 emission by 2050 if the cost of the modifications are too high?
Oh, that's a great question. And it's a real world question. We looked at, decarbonization of Seattle School District. It was somewhere between $500 million and $1 billion to do that, for all of their buildings. And that's one thing that school districts don't have a lot of, is funds to go around. So, where does that funding come from? That's a big question. The same thing, the city of Seattle. I'm sure a lot of different owners are kind of trying to answer that question. Where does this money come from to do all these things? The politicians put out the mandates of, thou shalt, reduce CO2 emissions, but where does that money come from? One option, what we've seen in Washington State, is a carbon tax where emitters over 25,000 tons of CO2 have to buy carbon credits. And as they buy that carbon credit to offset their emissions, the cost of those carbon credits goes to the state. And the state then invests in, in transportation, buildings, and that sort of thing to decarbonize their infrastructure. So there's a few different states going down that road right now. But yeah, the private sector, there's some large companies that have the funding to do these things, and they're committed to it. And I think on the state level, they're starting to put limits on what, your emissions can be. And it's kind of up to the owner to find that funding. And that's going to be tricky. It becomes a question of, are you going to pay the fine, or are you going to invest in your building? And, that's not an easy choice. And they're not small dollars we're talking about either.
Perfect. There's another question that just came in by Ahmad. He says, regarding issues with chiller heat recovery, you mentioned not enough load for the heat capture. Can you clarify what fixes CX team was able to achieve to utilize the heat?
Yeah, there's heat recovery chillers. We see those trip out often. And it's usually due to low source load. If you're making heat or something like that, and often they're connected to maybe a data center or a data closet, your IT load, something like that. And what's kind of promised in design versus what shows up in the field are vastly different. Maybe there's some exhaust heat recovery they have in a laboratory or something like that. But I think that base load, often what we see is maybe the design was over ambitious for how much base load they had to run that machine. And also staging, different loads can happen. We've seen a few dehumidification projects where the dehumidification mode turns on, where you have to reheat, but it's a big jump in what happens with the heat recovery chiller. So there's some timing issues. How do you, those chillers don't move very quickly, but the building wants to, those valves are going to move quickly because they're going to try to maintain space temperature. So you've kind of got to balance, you've got to slow everything down to get there. But yeah, it's, and we've seen some projects where the silver bullet is to put in a heat recovery chiller and they install it, but they don't spend a lot of time on the operations of, okay, how does that impact the rest of the building? So I think us as commissioning providers, as a control contractors, kind of that team, need to come together and really work out, what happens in total to these buildings. Because it's, small differences on set points, changes can really, wreak havoc on those heat recovery chillers.
Wonderful. So get this. While we still have another 5 minutes, I think we're up for another one or two questions, and I see another one just popped up. It's by Jared. He says, "Has the skin load reduction due to rooftop solar been considered in analysis?"
Yeah, I mean, I think it should be. I mean, I'm not sure, what buildings have or haven't, but from an energy modeling standpoint, yeah, I think it has. We've seen essentially large umbrellas put over buildings that they may extend beyond the footprint of the walls, but just to provide that external shading. And we've certainly seen that included in load calculations as well, and it makes a huge impact, especially if you have a significant gap between your roof or your walls in that kind of umbrella, if you will. That can really reduce the load in the building. We see that in a lot of zero or carbon neutral projects. You'll see those sorts of designs.
Perfect. And with that, I see that all the questions here have been answered. I'm just going to go ahead and use one of the sample questions here. How can we motivate building owners to invest in the systems in their communities?
Yeah, I think that's a great question too. How do you get owners to act? And I think it takes a little bit of political willpower, to meet that code. Code becomes a big deal. As codes get more restrictive, it forces owners to do that. So we're seeing that in a few different areas. We see it in California, Washington, Oregon, Colorado. Washington, D.C. has building performance standards that they're saying, your building shall comply to whatever the standard is, or pay a penalty. So I think that's motivating for owners. Probably not what they want to do, but I think the political willpower is there. We'll see what happens on the legal side of that. I think more to come there.
Wonderful. Thank you so much. And just the last question, or I think we should be good for now. Brandon, yeah, thank you so much for advancing to the last slide. So, well, I would like to thank each one of you for joining us for the webinar today. Thank you, Brandon, for such an informative webinar. It was packed with information. And with that, we would like to invite each one of you to join us at CX Energy 2024. That is the #1 conference and expo in commissioning, energy management, and building technology. We're going to have webinars. We're going to have, not webinars, I would say presentations. We're going to have networking sessions. You will be able to connect, network, and earn CEUs. So this year, we head to San Diego from April 29 to May 2nd. This is your opportunity to connect, network, and earn CEUs. For more information, just head to www.cxenergy.com. With that, you should be able to grab all the information that you need, and with the location, what exactly would be happening at the event, and all of those things. With that, thank you, everyone, and have a great rest of your day. Thank you, Brandon.